Hello, and welcome to this film about soaps, and more specifically about how we make soaps and how they work. Um, a lot of what we cover here is based on ester hydrolysis, so it'd be great if you've watched the film about ester hydrolysis before you start this one. Um, but hopefully by the end of this film, you'll be able to understand why a fat molecule ought to be able to be hydrolyzed just like any other ester. So in other words, you can understand why a fat molecule is an ester. And then once you've hydrolyzed your fat and produced the products that you produce, you might consider how those products will interact with different types of molecules and how that can explain how the soap works. Okay, we'll also hopefully know the difference between a detergent and a soap. Now let's start off just by looking at a fat and considering why it can be called an ester at all, and in fact why it can be called a triester. So here is a fat molecule. Once again, they tend to be quite large molecules with these very long carbon chains attached via ester groups. Okay, so here are three ester groups, hence they're triesters, and they're attached by these ester groups to a carbon backbone here. Okay, so that's a reminder of what a fat looks like. Let's have a think about what will happen if we break it down or hydrolyze it. Now, hydrolysis of fats specifically is called saponification because it results in the making of soaps. Okay, apparently this was done, well, we think by accident when ancient civilizations would boil up animal fats and end up breaking them down into things that worked quite well as soaps. Okay, so let's think about what happens when we hydrolyze a fat. We'll break the ester bonds. Okay, we'll put hydrogens back on the alcohol and we'll put the OHs back on the carboxylic acids. What do we need in order to do this reaction? Well, we need hydroxide ions, as we saw in the ester hydrolysis film. But there's three ester groups here, so I'll need three of them to hydrolyze one of these fats. Okay, and the products of this reaction, well, I'll have CH2OH here, CHOH and CH2OH. So I'll have that molecule, which is actually called glycerol, but it's not an important molecule to remember the name of. Okay, so there's glycerol. There's the alcohol that we make by hydrolyzing this ester. And the question is, are we going to make this fatty acid? So remember, a fatty acid is something that has a carboxylic acid at one end and then a big, long, fat-soluble carbon chain. It's fat-soluble because it's not polar. Okay, are we going to make that fatty acid? Well, no, because remember, every time we hydrolyze an ester, we don't make the acid, we make the salt of the carboxylic acid. So instead of making this molecule here, I'm going to make three, because there's three of them, I'm going to make three of that molecule without the acidic hydrogen at the end, because remember, that acid, if I formed it, would just react with more base. Okay, so I'm going to make three of this fatty acid salt molecule, right? And this salt of these fatty acids is excellent as a soap. This thing I'm circling here in blue, this is our soap. Okay, now why should it work as a soap? Well, let's have a look at the structure of it and how it might interact with water and with grease. Okay, now bear in mind, if I'm trying to wash some grease off something, it's normally on the surface. Okay, and grease doesn't like mixing with water, okay, because this is very polar and this is non-polar, right? So we don't get any significant intermolecular interactions between these two things. But if we look at our soap molecule, so here is the salt of a fatty acid. We've got a non-polar tail here, and because it's non-polar, it hates dissolving in water. It's called hydrophobic. It hates water. But at the same time, in the same molecule, we've got this ionic part to the molecule, which can form ion dipole forces with water, which are very strong. And so this part of the molecule is very water soluble indeed. In fact, it loves water and it's called hydrophilic, water lover. Okay? So because it's got a hydrophilic and a hydrophobic end, or a water insoluble but fat soluble end, and a water soluble but fat insoluble end, then this molecule can minimize its unfavorable interactions with water by burying the part that dissolves well in fats in the grease. Okay, so the tails get buried in the grease. The heads, these ionic heads or the hydrophilic ends, they stick out of the grease because they like dissolving in water. And then we can actually maximize the amount of contact that there is between these polar ends of the molecules and water, and minimize the amount of contact between non-polar molecules and water by forming these kind of structures, which are called micelles. Now here's a fat droplet now which has been pulled off the surface. It's being surrounded, or its surface is covered in these hydrophilic heads. So its surface now appears very soluble in water, and at the same time the soap molecules are managing to avoid being anywhere near the water by burying themselves in the oil. Now this thing here is called a micelle, and if you turn your fat or your grease stain into lots and lots and lots of these, well then you lift it off the surface and you clean your substance, whatever it is that you're trying to remove grease from. Okay, so by considering the intermolecular attractions between our soap and the grease and the water, we can explain how a soap does its job. Now we're just going to finish off by looking at the difference between detergents and soaps. Here is another diagram of a soap. It's called sodium because it's got a sodium ion here, stearate because this long molecule here is called a stearate ion. Okay, so once again we can see this part of it that loves water and the part of it that hates water. Now the trouble with these molecules, with soap molecules, is that when they encounter ions like calcium and magnesium, which you can quite commonly have in your water supply, they form insoluble compounds with these. In other words, they'll precipitate out, and that precipitate is called a scum. And quite often if you get out of the bath and the water seems incredibly dirty, it's most often because there's a lot of scum in the water and your soap has formed precipitates with these ions. Now that's bad if you want your soap to do any cleaning, because if it's involved in a precipitate, then it can't be carrying out its cleaning action. The nice thing about detergents, which instead of having the salt of the carboxylic acid at the end, have these kind of groups at the end. The nice thing about these is they still have this hydrophobic tail, they still have this hydrophilic head, but they don't form precipitates with the ions that we often find in water. So they don't form scums. And that's a major, major advantage of them because they continue to clean things even when there's these highly charged ions that tend to form precipitates. Okay, now if you remember, we said at the start of this film that we hope to understand why fat molecules could be hydrolyzed just like any other ester, why once we've broken down a fat, why the molecules that we end up with are quite good at forming intermolecular interactions not only with water but also with grease molecules, and understand why that helps them clean. Okay, and we've just finished up by talking about the difference between detergents and soaps. As usual, any questions or comments, either come and see me or post a comment on YouTube.